Hello and welcome to the recording of the virtual meeting DelocChem on synthetically useful reactive intermediates. I was delighted to host this meeting with three amazing speakers and generally amazing scientists on the 20th of June in 2020. I'm glad that we have been, and you are now by watching this, part of the global push towards a more sustainable scientific exchange with reduced amounts of unnecessary travels. First up, we have Privatdozent Joachim Ballmann, who studied chemistry at the University of Erlangen, then moved on to do his PhD with Frank Meyer in Göttingen. In 2009, he moved as a postdoctoral fellow to the University of British Columbia to work with Michael Fraser there, and then returned to Germany to do his habilitation, which he finished at the Heidelberg University in 2018, where he is now still a independent research group leader. He's mainly working on novel phosphine ligands, especially in conjunction with early transition metals. I hope you'll enjoy his talk. The stage is yours, Joachim. Thank you for being here.
All right, so first of all, sorry that I don't have a camera connected. I left that actually at the university and I don't have a built-in one in my laptop. And I am in the reactive intermediate session, and we will hear about reactive intermediates, and the red line sort of through the talk will focus on the chemistry of diphosphinotolanes. So these are these molecules over here. And as we will see, we will hear from Pincers to Carbenes all the way to organic materials. So first of all, I would like to start with a very brief introduction on how or why people would be interested in diphosphinotolanes, why we are interested in these. And for that, I have to look into a broader picture, namely in broader phosphine ligands, in particular diphosphine ligands, the one with large bite angles, trans-spanning phosphine or large bite angle phosphines. And you probably are familiar with all of the ones you see in the top row, maybe not the middle one, but at least xanthos and DPPE derivatives. And yes, they have this large bite angle, some of them close to 180 degrees, but there's a very important feature that is also present in most of these large bite angle phosphines, and that's that interaction with some central element in that bridging unit that links the two phosphines. And here it's the oxygen coordinating to the rhodium, or here it's the iron which may coordinate to the palladium, and here things you probably won't even expect at a first glance, the agostic interaction with the iridium here. And of course, these interactions, all of them, they modulate the electronics at the metal. And in view of the wide use of all these species, it's actually surprising that the ligands in the lower row, these three, they haven't been used that widely. And it's surprising because the bridge elements here are fairly simple. That doesn't mean that the ligands are simple to make, but the bridge elements themselves, like the benzene, like alkene, alkyne, it's simple unsaturated organic molecules that modulate the electronics of the central metal. And that one here is particularly underdeveloped, these diphosphinotolane ligands. So basically, this one researcher from Japan, he prepared a rhodium and an iridium complex of this type, and it hasn't been yet used in catalysis. And of course, you should ask the question, or you may ask the question, why is that so? There might be a nice modulation of the metal, but of course, we all know that alkynes are substrates as well. And there are whole books about the chemistry of alkynes, and that's actually what was observed here. So when they prepared, in the OA group here in 2012, prepared that rhodium-1 species and heated that up, they observed the typical cycloaddition chemistry of alkynes, and they isolated that cyclobutadiene species here. So that probably explains why this ligand hasn't been more widely used, but you may, of course, think about ways to correct that. And we start here with this rhodium complex somewhere in the middle ground. So that species was assigned to a rhodium 1 oxidation state with a coordinated alkyne as a 2-electron donor coordinated. And of course, you can think how you can circumvent the alkyne taking part in catalysis. And one way is to go all the way to that end, which means you sort of remove the alkyne. That way, of course, you make it less activated in that stage, but eventually you will end up with the alkyne simply as a space holder. That's probably not what you want. Otherwise, you could also use other building blocks. You want that interaction. And the interesting way to go here is not to bring the alkyne away from the metal and make it a less activated alkyne, but bring it even closer. And when you bring it even closer, the alkyne will be more strongly bound to the metal in the sense of an oxidative addition. And that way you might hope for, and that's what we were hoping for, that it doesn't take part in a reaction anymore. And you can even go to these ones, species which the alkyne is it's a metallocyclopropene then, and it can serve as a 4-electron donor. So you can even imagine that one being a 2p aromatic system. And the way you got to do that is you have to actually go to the early metals where these oxidation states are easily accessible, to higher oxidation states. And these are all known for forming very stable metallocyclopropene derivatives. So that's where we started with our chemistry. So these are pretty reactive molecules: titanium in the oxidation state 2, vanadium in the oxidation state 2, and molybdenum in the oxidation state 2. That one is not that reactive, it's CO stabilized, but the other two, you actually need a ligand to stabilize them. And you see that at the reaction temperatures, you need to keep it at low temperature all the time until you isolate these complexes. And once you isolate them, you see it fits to the title of the seminar series, DelocChem. So this is a perfectly delocalized backbone here. It's nearly planar in both cases. So you arrive at the titanium 4 or vanadium 4 D1 species. Here you see a deviation from planarity. You have that bowl-shaped structure, but this is mainly to the coordinated CO. We can also make that complex without the CO, and you will have a perfectly flat backbone, which is best described as a metallocyclopropene. So, of course, the question arises, are these complexes still reacting at the alkyne, at the coordinated alkyne or metallocyclopropene? And the answer to that is no. So it actually works. So these are now ligands. They are not fancy substrates anymore, and they don't react at that alkyne, coordinated alkyne moiety. And this you can, for example, show by simply coordinating an isonitrile. Isonitriles are known to insert in metal alkyne bonds. In that case, it won't insert, it simply coordinates. You can alkylate them, and this is particularly surprising. The alkylation, it works cleanly, takes part only at the metal, no attack at the alkyne. If you react the free ligand with that particular lithium alkyl, you actually observe addition of the lithium alkyl across the CC triple bond. And sure enough, you also can reduce, and now you will see that the backbone flattens in completely. No CC coupling at the alkyne, it's metal-based reactivity. So, and I would like to focus a little bit more in on the group 5 chemistry, so because this reaction actually is particularly surprising. As I said, you take the free ligand, react it with the alkyl, lithium alkyl, and you observe direct attack at the alkene. And I'm going down the row here to niobium and tantalum, both complexes here in the 5 oxidation state after these sort of oxidative addition. So you end up with perfectly diamagnetic compounds, D0 configured, again, these flat backbone. And once you isolated these species, so you still have to keep it at low temperature while you make them, but once you isolated the complexes, they are fairly stable. And once again, you can alkylate them, and when you alkylate the same precursor as we saw for vanadium, you straight go to the alkylidine species, so the tantalum C double bond here. And once again, this species is fairly stable. You can heat that up 70 degrees. Remember, this was the conditions where the rhodium species in 1 hour underwent the cycloaddition chemistry, the cyclobutadiene. Here, 24 hours, you can use that in catalysis, and of course, only 1 mole percent of this catalyst. And of course, after 24 hours, you can add some more substrate. It still is alive, the complex. You will still go on with the polymerization reactions. So these concepts work. You can stabilize usually rather reactive fragments by coordinating the alkyne to them. Of course, there are borders of stability, and one of these borders we discovered when we looked into hydrogenation reactions. So this is pretty tough to hydrogenate. Naphthalene derivative, it works, but only with 30% yield. So of course we pose the question, what's going on there? If you run it longer, yields won't improve. If we add more catalysts, catalyst loading, yields will improve slightly, but not dramatically. And we figured out that after 3 days, or after 1 day, so in these conditions, basically you have more than 50% conversion already to that tantalum 5,5 complex. So here we reached the borders of stability. No cyclopropene anymore, no metallocyclopropene, but a metallocyclopropane. So that underwent hydrogenation here, and we arrive at that particular tantalum complex, and that one is not active. So if you isolate that one, it's not active in the hydrogenation catalysis. And I will have a closer look briefly on that species. It's a very interesting species, fairly reactive. It has overall 6 hydrides, 3 in the bridge, 1 tantalum equipped with 2 hydrides, another one with 1. And they are aligned along the 3 axes in the coordinate system. And it is, to my knowledge, the only tantalum hydride which actually appears, or one of the hydride appears in the negative region. So tantalum hydrides usually appear in the positive region, here or here. But this particular hydride, which is moved in between the 2 phosphines, or within the same plane, it appears in the negative region. So that compound is particularly interesting on its own, but we are, of course, working on isolating or trying to get a grip on these species which we believe are the active species in catalysis, particularly that one, by increasing the steric bulk. So these complexes, we are still working on isolating these really reactive species by installing adamantyls here, but overall, these motifs are stable with exception of that tantalum species. So we were going from that middle ground here to that side, and of course, to prove the principle, you should actually go the other way. And that's what we did. We also checked what's going on the other way. If we actually move the metal, or we use a metal in that block, that we should end up with a pretty activated alkyne, which will undergo a reactivity at the alkyne. And rhodium, that was the work by Owen. So we decided, of course, to move one step further and go to palladium, also interesting in terms of catalysis. And sure enough, what we observed when we reacted with various palladium zero precursors, it doesn't need to be the DBA species here, but we react them 1-to-1. It also can be a phosphine stabilized palladium zero. What we get is these palladol species here, and along with palladium black. And this is true for almost every palladium zero species. There's just one exception that we discovered so far, and I will show that in just a few seconds, but usually you end up with that palladol species. You can, of course, also make the pincer type complexes, so the precise analog of the rhodium species that was known, but you have to, pay attention with the precursors you use. Actually, you need to have a precursor with just 1 chloride coordinate to the palladium and a non-coordinating counterion, so you can access these pincer type species. You have to handle them with care. As soon as you have excess halide around in solution, like if you simply add palladium dichloride, acetonitrile added to the precursor, you will end up with a vinyl palladium complex. You observe straight carbopalladation. And yeah, you see the two crystal structures. Of course, once you have that one, these fairly reactive intermediate, you can quench that with excess chloride, PPN chloride, and you will go here. Interestingly, you can go back. So cleaving the CCl bond, covalent CCl bond is possible with silver PF4. Good, I mentioned that there's one exception in the palladium zero precursors, and this exception is shown here. It's the isonitrile coordinated species, but you have to be careful with the stoichiometry. You need to use two equivalents to get a clean reaction, and what you get is that unique palladium-1 dimer. So there are numerous palladium-1 dimers, but usually they are halide bridged, and that one is one of the only ones out there which is bridged by an alkyne in that particular fashion. So with the palladium, two palladium atoms and the two carbons of the alkynes close to being plane. So there's of course a slight twist in there. You see that C2 symmetry, the axis reaching through that to the spot of my laser pointer now. And the electronic structure is also best described as shown in this Lewis formula here. So you have a double bond in the backbone as indicated by IBO analysis, and you also have this metal bond here. So we are currently still working on reactivity studies. The species, for example, reacts with CO, and we are pretty confident that we can use it in decarbonylative coupling reactions. But we stumbled across something actually more interesting. And so that one had to wait a little bit, because what we found is that reaction here, when you react that precursor with allyl palladium chloride, you end up at that particular species. And of course, a lot of questions arise. So basically what happened, the phosphine of the own ligand, it attacked at the alkyne. So it bit in its own back. Similar to the chloride attack here, it's just not externally attacking the alkyne, but it's internally attacking the alkyne. And you will arrive at that structure. And there, of course, there are a lot of questions associated with that structure. Reversibility, like we saw in that case. What is these dotted lines actually? So I didn't tell you yet what represents it. Is it a carbene, or what is that? Is it more general? Is it limited to palladium? How does that react? And I'm going to focus in on these two questions. What is it? And is it more general? And answering the second question first, is it more general? The answer is yes, it is. So basically, it's all these red elements here in the table. They form species of that kind. Going from hafnium over molybdenum till gold 3 here in that corner. And when you look at that picture that emerged from our screening studies, you can already guess that these species in the middle of the block here, they are more stable. We get, for example, for group 6, we can isolate all these species for all the triad, while for gold, let's say we really have to struggle to get that species. It's only available for gold 3. So, and you see in these two rows here, we needed a long time to actually access two species, but we finally managed to get a zinc compound and the yttrium compound, both shown down here. It's all crystallographically characterized, of course, and I will come back later to these two species shown here. But at first, we should answer the question, what's the principle behind it? So are we just dumping some precursors which we have sitting around the lab on that ligand? No, we are not. There's a logic behind, and I would like to explain this logic with a manganese example here. So what you basically need is a metal precursor which has two open coordination sites, and they need to be strictly cis positioned to one another, and there shouldn't be a third one in the next cis position Otherwise, you will access pincer type species. But if you have exactly 2 open coordination sites, then, like in that example for that manganese species shown down here, where you can replace the 2 pyridines, you can form a species coordinate via one of the phosphines and the alkynes. And you can rewrite that in a very fancy way. I admit that it's a fancy way to rewrite the alkyne that probably does not, or most likely does not play a role in the ground state. Excited states can be dicarbenoid, but the ground state for sure not. But it's a good way to visualize what's going on. So the phosphine here, the free one, can actually attack at that p orbital of the carbene. We envision it as a carbene for now, and when we envision that, we arrive at least at a reasonable first assumption for what these dotted lines mean. So one resonance structure to represent these dotted lines is the one shown here. Good. Once you have this one resonance structure, it's the one in the middle here, you can, of course, think about a lot of others. For example, these mesoionic ones, carbene one, or these vinyl resonance structure. And we have crystal structures of all of, or most of these species, at least one example for each group here. And when we analyze the elliptic bond lengths, these PC bond lengths here, and compare it to the one over here, we find that this elliptic bond here is in the range of a typical single bond, while the CC bond here, that one here, is in the range of a typical double bond. So basically, you can take out these 2 resonance structures right from the beginning, and you have to focus in on these 2. These are, on basis of crystallographic data, the most reasonable ones. So what is it? Mesoionic carbene or phosphindolium zwitterion? So these are the 2 resonance structures which are remaining from our analysis. And to answer that question, I brought a few examples, a little bit of everything I have to mention. It's a 5D0 metal here, hafnium. It's a 4D6 and a 3D10 in the thing. So we have D0, D6, D10, 3D, 4D, 5D, and we can start a closer analysis. And I would like to begin with the molybdenum in the middle ground. So 4D6, and we know already single bond here, double bond here. All we don't know is what is about that dotted line here. And of course, you can have a look at MOs, NBOs, NRT, IBO analysis. And what you actually see in these analyses is you have a sigma symmetric bond, single bond, and you have sort of a pi back bonding interaction. Actually, 2 of them, which can be described also as 3 center 4 electron bonds. But of course, what you don't know yet is that the back donation, well, you might estimate from the IBO output where these orbitals are localized, but there's another way to do that. This is energy decomposition analysis, and here you see the deformation densities in the EDA NOF-CV analysis, and you see the charge flow from red to blue, so from the d orbital to the carbene C. And there's a nice paper by Franking recently giving details on how to distinguish these on basis of that numbers, and it clearly is the mesoionic carbene structure which we have. And this is valid for most of the, or all of them in the middle of the periodic table. So once you go to the very end or very edges, to the early transition or late transition metals, it's less clear to distinguish between both of them. In the IBOs, you only see the sigma interaction. Energy decomposition analysis, well, you see hyperconjugative stabilizations here, which is common from either from the sulfides or from the chlorides. So this is the zinc complex here, but you observe the same in the hafnium chloride, a hyperconjugative interaction with the carbene, which is also found in NHCs. But on basis of that, you should not judge on it. What's a good way to do it is topological wave function analysis, so quantum theory of atoms and molecules here, Bades analysis, and you can have a look at these bond critical points, and there's a lot of values associated with that. I just brought 2 of these values, and the positive Laplacian here and where it's located closer to the metal, which is common also for vinyl sinks. But this picture here is in favor of the mesoionic carbene structure, slightly at least. So we can conclude that basically all over the block, the mesoionic structure is the favored one. Good. I promised you that I will come back to the edges because we're talking about reactive species, and the yttrium and the zinc, these are the particular reactive ones. You really need patience to isolate them. You need to keep these complexes all the time at low temperature. You need to keep them away from donor molecules. And the problem with these two species is the phosphine, the second phosphine here. Let's focus over here. Here it's more clear. That phosphine is decoordinated in solution. So for zinc in the solid state, it's still bound to the metal, but only in the solid state. In solution, it's decoordinated. And for yttrium, situation is even worse. It's even decoordinated in the solid state. So you have only that mesoionic carbene bond attached to the metal, and the phosphine is actually dangling. And this is what happens if you don't keep them at low temperature, or you don't keep donor solvents away. So this will turn nice and green in both cases. And based on these decoordinated phosphine, you can already assume what may have formed. So starting again here from our proposal, how to form these species, and focusing in on that equilibrium where the phosphine may dissociate in solution, you of course end up with the problem as the phosphine can attack again at the empty p orbital of this carbenoid carbon here, and that will eliminate the metal, and you will end up with a diylite type structures. And indeed, these green solutions are the diylites here. And this you can make more easily even without a catalyst. Then you need to heat it, but you can also use zinc or yttrium as catalyst to arrive at these deep green solutions. And I think I don't want to go into much detail about the aromaticity and resonance structures, just one brief word or one brief sentence. So this is the most likely resonance structure, which also reflects the calculated in the crystal structure distances. So you see that one here. It should be an aromatic bond C2, C7. It's 1.44. So it speaks for these allylic or benzyl anion structures in these molecules. So these are deep green species. You have to keep them away from chlorinated solvents. You have to keep them away from acetone, or you will arrive at addition products. And the title of that slide doesn't really fit. It's a air sensitive compound, so it's not really a material. So we decided to make it a material by oxidizing it, and you have to do that in that particular case. It works for the phenyl as well. For the isopropyl, I'm going to focus in on the isopropyl. It works best in two steps. So you can first oxidize to the monocation. It's not shown over here, but it's the structure over here with just one chloride counterion. You get a nice EPR signal, but it's still air sensitive, so still not what an organic chemist considers a proper material. But you can also doubly oxidize it then in the second step, and you will end up with a bright yellow air-stable powder soluble in water. It has a nice blue-green fluorescence, and that's shown here not only for the isopropyl version, but also for the phenyl version here with R equals phenyl. So the uncharged diyelate, the monocation, and the dication, and they are all still here under the UV light. You only see the dicationic species. And what's particularly remarkable, they have a pretty decent quantum yield in water, so 74% in water. That makes these species interesting not only for organic materials in the sense of orthogonal solvent deposition of multi-layer devices, but it also makes them very interesting for biological applications. And that is actually currently supported by the Vector Foundation. And with that, I would like to sum up. I'm already briefly or shortly over time. So we have seen that these species, with the right strategy, you can convert them to very stable PCCP pincer type complexes, which you can heat up to 70 degrees for hours and use them in ROM catalysis, no decomposition. If you heat these species up just in the absence of a metal or in the presence of zinc or so, you will end up at these diilids, which then you can oxidize to the materials. And there's a really nice chemistry of mesoionic carbenes, where I didn't tell much about catalysis yet, but we are examining these species and reversibility of these bonds. So it's a new class of mesoionic carbenes. And we also found a new motive in palladium-1 chemistry, which we are going to exploit hopefully in catalysis soon. And with that, I have to not only thank the Vector and the DFG for giving the financial support, but also all the people who actually did the work and the collaborations, and of course you for your attention. And with that, I'm stopping and I'm open for questions, of course.
Great, thank you, Joachim, for this nice walkthrough. All of transition metal chemistry, basically. Yeah, please post questions in the Q&A section and use the raise your hands button if you have a question. Apart from that, I was wondering, Joachim, you're working with like both ends of the transition metal rows there.
Yeah.
Could you give people a short overview about how it is different to work with the early transition metals as opposed to the late stage, later ones?
Yeah. So, well, the very first difference for a PhD student entering the topic is probably when a reaction goes wrong. That sometimes is the case. It turns black for the late transition metals. So probably people working with late transition metals have observed that you get a black mirror of some elemental metal depositing, sometimes nice nanoparticles. So reduction to the metal, that happens in late transition metal chemistry. It usually does not happen in early transition metal chemistry. So if your reaction fails, your reaction usually turns white. And this is because of the high stability of hydroxo anions, oxides, and halides. So you favor the higher oxidation states. And that's basically the major difference. The higher oxidation states, these are the favored ones in the early transition metals, while the lower ones are more favored for late metals. And these favoring these high oxidation states, in particular in combination with oxoligands or oxide derivatives, makes these compounds of early transition metals very sensitive towards water. So you have to keep water out at all stages, which also limits somewhat in the catalysis you can choose. So you should not aim for catalytic applications that liberate water when working with early metals. While this is not a big issue in the most late metals, of course, this is very general speaking here. Usually these tolerate water more easily. In terms of oxygen sensitivity, you should not distinguish. They are, for both of them, for early and for late, they are very oxygen sensitive species. But aqueous sensitivity, it's a real problem in the early metals. Yeah.
Right, cool. Thanks very much. And we are still missing our first speaker, so we will sadly have to continue our schedule for now, and hope I can reach him in the meantime. I'm not sure what's happening there. Sorry about that. But correct. We next up have Mu-Hyun Baik from the KITE. Wait a second.
Okay.
Right. So Mu-Hyun Baik was born in Seoul and grew up in Germany. Actually, he's speaking German perfectly fine. We had a little chat in German earlier. after he started studying chemistry or studying in Düsseldorf, he moved on to the UNC Chapel Hill to obtain his PhD there in 2000. In 2003, he started as his independent career at the Indiana University Bloomington, and later returned home after 12 years to Korea, became professor at the KAIST and associate director of the Institute for Basic Sciences. And he's doing pretty cool computational molecular modeling, and also actually experiments in some really nice physical chemistry that we're going to hear about today. Stage is yours, Milky. Thanks for being here.
All right, thank you very much for that introduction, and thank you for having me. It's a little after midnight here, so I'm going to try to stay awake here. I think I'm going to do okay. All right, let me see if I can share my screen. Okay. It almost feels weird to be talking to a mostly German audience in English, because ich spreche fließend Deutsch. Ja? Wir könnten das Ganze auch in Deutsch machen. Okay. All right. Let me see. Can you see my screen? Can you see it moving?
Yes, perfectly fine.
Okay. All right. So what I thought I'll tell you a little bit about this work that we have started doing earlier. I know this audience is mostly organic, so I'm going to talk about a new effect that we discovered that I termed electroinductive effect, a new way of controlling chemical reactions. As Florian has already indicated, I was these are my life stations. It's a little bit unusual, so I'd like to share that with you for a few minutes. I was born in 1970, and then I spent the first 10 years in Korea, in Seoul. And then 1980, I moved to Germany because my whole family moved there, so I was 10 years old. And so I spent then the next 15 years in Germany, in the area of Düsseldorf, where I also did my undergraduate work. And in 1995, I moved to the United States to do my PhD, and I postdoc at Columbia University in New York. And then in 2003, I became an assistant professor at Indiana University in Bloomington, and I was promoted to associate and tenured there. And I was basically ready to retire in the United States. Although I was born in Korea, I didn't really have a lot of connections to Korea, and I didn't really particularly feel Korean. If I had to pick a country that I would call home, it would probably be Germany, because I spent, of course, my most important years of my life there. So as you can see in this, I spent 10 years in Korea, 15 in Germany, 20 years in the United States. And then in November 2015, I moved back to Korea because KAIST made me an offer to be a professor here at KAIST in Daejeon, where I have been since. So I've been a little over or almost 5 years here. So I wanted to take a minute or two to tell you about the Institute for Basic Science, because this is a little bit new. KAIST, so this stands for Korea Advanced Institute of Science and Technology. It's a technical university, and it's been around for a while. So many of you may know this institute. But this Institute for Basic Science, which is actually a new entity, it's going to be interesting for many of you who are in science and who are actually moving forward, because this is, I think, the flagship of the Korean development in science. As you might have noticed, while the United States and Europe has been cutting funding into sciences and things have been stagnating a little bit, China and Korea has been growing aggressively. And today, Korea actually invests about 5% of our GDP into research and development, which is almost twice of what Germany and the United States and all the other countries actually do. So Germany is, I think, at 1.8% or 2% or something like that. The United States is at about 2%. Korea is at about 5%, which is a little over twice of what the government invests. And the IBS, so Institute for Basic Science, is actually one of the beneficiary of this new policy. And it's meant to be the Korean version of let me get my screen here. Okay. So the IBS is meant to be actually the Korean version of the German Max Planck Institutes. And for many of you who are aware of actually the privileges that the MPIs enjoy, we actually get to have most of those. It's a little bit different than the MPIs, but we get most of the benefits of the MPIs. They really wanted to create a dream institute for scientists. They're envisioning 3 to 4 directors in each institute and about 5 junior groups within an institute. But the directors basically have a lot of freedom to do whatever they want, basically, which is exactly the system at the MPI. The total funding for each center is about 10 million per year, and it's guaranteed for 10 years. And there are no proposals, no restrictions on research direction. There are no short-term benchmarks, and it's intended to be continued indefinitely. So this sounds like some serious commitment, and it is, right? So each director and an associate director is envisioned to have around 10 postdocs and 30 graduate students. And they are supposed to pursue basic research without any limitations for need or any kind of justification. Currently, there are about 30 IBS centers, 6 of which are in chemistry. And the budget of the whole thing, that's about 30. And then some of these centers actually have heavy equipment needs, like some of those physicists actually need gigantic instrumentation. So their budget is actually a little bit larger than ours. So overall, the budget in 2019 was 477 billion Korean won. So that's about 406 million US dollars between the 30 centers. So this is actually really a serious commitment. And so in the last 5 years, I've been able to, I was lucky to recruit actually a pretty large group. So I wanted to do the acknowledgement of my students first. These are actually my graduate students. These graduate students in gray are alumni. So these are students that I had over their 12 or 13 years that 12 years in the United States. And these are now mostly my Korean graduate students that I recruited over the last 4.5 years. So I have a group of about 40 people now. Okay, so enough of the introduction. I wanted to actually talk about the science. I started out thinking, because the government was telling me I can do basically whatever I want to do, I wanted to think about something that's a little bit more fundamental. Many of you who may be familiar with some of my publications know that I'm actually a computational chemist. And I'm very much interested in electronic structure and reaction mechanisms. And so what Joachim just talked about is basically actually what I've done in the United States, thinking about actually the bonding, about actually transformation of ligands, redox non-innocence, and all these things were actually what I've been doing in the United States. And that's still what I actually continue to do. I mean, but this project is something that I started with a handful of students, and I said, let's do something completely different. And let's more fundamentally think about how we control chemical reactions. And we can, of course, talk about chemical reactions and the way chemists control chemical reactions without looking at the Hammett parameters. And here I actually show a picture of Lewis Hammett, who introduced this concept to us that you can use functional groups to control chemical reactivity. Now, this has been known forever. Lewis Hammett didn't invent this, but he was the guy who actually kind of brought order to the system and actually provided a framework in which you can think about it. And what he has done is he basically shown that you can take a very simple reaction, any kind of reaction, and by changing the electronic structure, by decorating these reactive cores with electron donating or electron withdrawing groups, you can actually change the rate of a chemical reaction. And so this is actually the famous plot, and he published this in JACS in 1937. And so to be just on the same foundation, let's actually look at a simple reaction that we're all familiar with, and that is something like a palladium zero catalyzed aryl halide bond activation, right? So this is actually what we would call an oxidative addition, where we are starting with palladium zero, and we're going to make two palladium carbon, palladium iodide bonds. So basically, we're going to need 4 electrons to do this. 2 electrons are going to come from this bond. So where we envision this aryl halide bond being cleaved, leaving behind basically an iodide minus and a phenyl plus. And the iodide minus, of course, can act as a Lewis base to donate into this palladium center to make this palladium iodide bond. Now, this is a standard Lewis acid, Lewis base type of interaction. No change in oxidation state. Yeah? The phenyl plus, of course, now needs to use the blue electrons. There's electrons that were localized on the metal first, and now they become actually shared between the metal and the carbon. And because carbon has the high electronegativity, formally those 2 electrons belong to the carbon. So when you do the oxidation state count, you will actually get palladium 2 for this species. And this is an oxidative, that's what we call an oxidative addition. And if you apply Hammett's principles to this reaction, you could envision taking one of these phosphines, triphenylphosphine, for example, and if you replace in the para position, if you decorate them with electron donating or electron withdrawing groups, right, which Hammett has showed us to actually quantifies in his sigma parameters, then what you see is, of course, that when you put electron donating groups on these positions, because you're doing an oxidative addition, the reactions usually become faster. On the other hand, if you actually place electron withdrawing groups like CF3 at these positions, the oxidation or the oxidative component of oxidative addition becomes more difficult, and so the reaction slows down, right? So when you do the Hammett plot, you're going to see a negative slope. Okay, so what we actually find from this is ligands with electron donating groups enhance the rate of oxidative addition. This is easy to understand. Okay, so this is actually just one example. I could actually go on to show you many examples where people have used functional groups to control chemical reactivity, right, and reaction rates. Now, I wanted to think about this thing that we've been doing for 100 years now, and critically evaluate, is this really the best way to do this, right? Is using functional groups like these to control chemical reactivity that I just discussed, is this really the best way to do this? And I would actually claim it's not. Why not? You know, there are many reasons why this is actually a pretty stupid way of controlling chemical reactivity. Number one, tuning is necessarily discontinuous. What I mean by that is if you look at actually the sigma parameters, they're necessarily going to be gaps. Right? So if you look actually, for example, this amine and this methoxy, there's actually quite a jump in electron donating ability. What if you wanted something in between? Right? Of course, there are functional groups that will have a sigma value between those two, but you would actually have to find them first. So that's actually not really very convenient. Substituents, of course, not innocent. What I mean by that is when you take this acyl chloride that we list with a sigma value 0.61, we list them because, you know, Hammett found them to be in the list, but they're really not very helpful because acyl chlorides are highly reactive. So if you put this on as a functional group, you don't really have to worry about the reaction that you're studying because you will get side reactions because of the acyl chloride. These substituents often change solubility of the molecule, so they crash out, and then you are screwed. Every molecule must be prepared. This is a nightmare called synthetic reality in chemistry, yeah? So if you want to, of course, study the reactivity of these molecules, you need to make dozens and dozens of these molecules. And I don't know how much time we as a chemical community have spent, and how much time we are actually still spending, and how much time we will be spending in the future to make functionalized derivatives of a reaction that we want to study just to understand the chemical reactivity. Now, you might actually say, well, what I just described is called chemistry. Yeah? So can we do better than this? And here is actually what we thought we should try. And I call this the electroinductive effect. It sounds like a word that you should know, but it's I made it up, right? So if you do on Google search on electroinductive effect, you'll find actually one hit, and that's actually a Chem archive paper that I submitted about a year ago that I posted in this archive to just communicate preliminary results. I need to, I was reminded by somebody that I should actually make clear that I did not invent the word electro, I didn't invent the word inductive, and I didn't invent the word effect, yeah? So if you do a Google search on electro, inductive, separate words, you will find electroinductive industries, which is actually apparently a company that makes transformers, right? So that's not what I'm claiming. I'm claiming that the effect that I'm about to describe is actually what I made up, right? I don't want to claim credit for stuff that I didn't do. Okay, so here's the idea. Instead of making a new molecule, could we immobilize the parent molecule onto an electrode? Yeah, like here. So you have the reaction site. You have a ligand. If we could immobilize this thing onto an electrode, could we dial in then the inductive effect through voltage? Okay. So imagine this reactive site would be the palladium set that I was talking about. And this ligand would be the phosphine, and we attach this to an electrode. And by applying a voltage, can I mimic the reactivity change at the reaction center that we actually usually probe by functionalizing, yeah, by applying a voltage? Why we would want to do this is actually, obvious now, because electroinductive effects are continuous. The problem that I described to you, that there are gaps between the sigma values, is not going to be here, right? We can change the voltage continuously. We can change it by very small amounts, right? So we can do whatever we want to do there. So if this worked, there would be no laborious synthesis of derivatives. We would actually make just basically one core. We could attach to the electrode, and we could probe for the reactivity of these inductive groups very easily. What is very exciting is we could actually vary the catalyst property as a function of time. So temporal variation of catalyst property would be possible. Because usually the way we are doing chemistry now is you prepare a catalyst with a functionalization that we actually went through, and then you run a reaction. Yeah? And that catalyst has to be in the reaction from the beginning to the end. It will not change its chemical property in the middle of the reaction. But with this new technology, we should be able to actually make the catalyst electron rich at the beginning of the catalytic cycle, and then make it electron poor towards the end of the catalytic cycle, because we can change the voltage, and we can easily invent actually on voltage cycle or voltage sequence, like we program pulse cycles in NMR, and that will allow us actually to change the catalyst property over time. Experiments that we have done actually show that the entire Hammett space, yeah, between T-butyl and trifluoromethyl or whatever, so these the entire Hammett space can be covered by about 600 millivolts. Okay, so what that means is we're currently limited, actually, the amount of voltage that we can apply is limited by solvent reductions, solvent oxidations, or other redox reactions of the substrate. So realistically, the actual operational window that we have available is about 2 to 3 volts. Okay, and so since the Hammett space is only covered by 600 millivolts, what this means is we should be able to make super electron donating or super electron withdrawing groups and actually study their effects on this catalyst. There are no side reactions. There are, of course, going to be side reactions, but what I mean by this is there are no side reactions due to the acyl chloride story, where you place something where you wanted to actually change the chemical reactivity. Instead, what you have done is you introduce a reactive functional group. Okay, so we are not going to do any of this. There are no solubility issues, because the catalyst is already immobilized. Yeah? And that, of course, leads to also operational advantages, like separation of catalyst and product is going to be easy. You pull the electrode out. Okay, so does this work? Right? I hope that I've convinced you that this is actually an interesting idea to try. So does this work? It looks too good to be true, yeah? Okay, so we need to do a proof of principle study. And my group decided that we want to actually go back to the 1937 paper of Hammett, because Hammett, you realize, was a great chemist, of course, yeah? And so he has used actually 39 different reactions to derive his sigma parameters. And these 39 reactions were hand-picked. Yeah, they are not air sensitive, they're not too slow, but they're not too fast. Yeah, they're easy to measure, yeah, they're easy to handle. And so we thought that's actually a great point for us to start. So we went through all 39 reactions, and one reaction actually caught our eye immediately, and that is actually this simple reaction where you start out with a benzoic ester, and then by exposing it to a base, you do a hydrolysis. So this is an ester. So this is a saponification reaction. This is a reaction that that many of you have done actually as undergraduates, right? You take an ester, base hydrolysis to regenerate actually carboxylate plus the alcohol. And so since we are generating a carboxylate here, if you put function groups here on R, that it's actually electron donating, then what you're going to get is you're going to slow down the reaction. That's actually exactly what Hammett saw. And so when you do on Hammett plot, what you'll find is that electron donating groups actually slow down the reaction, where electron withdrawing groups, by stabilizing the product here, accelerate them. Okay, so my two students, June and Jung-hee, looked at this reaction. And so here's what we're doing. We actually have the small vial where we're going to actually try to do this saponification reaction. We, of course, need to somehow covalently attach now the carboxylate or the ester to an electrode. And we chose to just use a gold electrode, okay? This is the gold electrode that we use. I went down to one of our electrochemists and asked them, I want to use on gold electrodes, so what should I do? And they told me, okay, the way we usually do this is you take a small piece of glass, and then you put titanium dioxide on the surface, because titanium dioxide is the glue to attach a very thin layer of gold, right? So you can make gold electrodes by doing that, right? And then gold actually sticks to the titanium dioxide, but it doesn't stick to the glass surface. So then you actually get you can make very cheap gold electrodes. We tried that. We are horrible experimentalists. It didn't work for us, right? In the middle of the reaction, the gold foil would come off, and it was a major pain in the ass. So I told my students, you know what? Why don't we go down to the jewelry store, of which we have many in Korea, and have them just give us a gold bar, right? The gold bar is not gonna, it's gonna be a little bit more expensive than this other thing, but how expensive can it be? And B, then we are not going to have any problems with the gold foil coming off. And this is such a gold bar. It's actually a centimeter wide, about 2 millimeters thick, and it's about, I think about, what is this? About 10 centimeters long. Okay, so this is what our gold or jewelry store, it's not even very pure gold. It's a normal gold that jewelry stores use. And then my students made this very unsophisticated way. This is just basically a copper wire, and this is basically Scotch tape, Tesafilm, yeah, to just attach the copper here. And then we have roughened this area here, where what we're going to do is we're going to actually make the thiol version of the reactant. Why the thiol version? Because if you have a thiol, it will self-assemble on gold surfaces, and it will make a very stable, very well-defined self-assembled monolayers. Okay, so we know how to do this now. So we actually get them in there, and then here's the ester. And what we're going to do is we are going to expose it to hydroxide, okay, so a potassium hydroxide solution. We started with actually a very diluted potassium hydroxide solution, but we figured out very quickly that this thing is very solid, it's very robust. So we actually increased the potassium hydroxide solution to a 3 molar potassium hydroxide solution. This is now a very concentrated potassium hydroxide solution. We settled on 50 degrees Celsius and steering it overnight for almost a day. And then in water. under vigorous steering. And so we're going to watch actually the saponification reaction. And what we're going to do is we're going to apply 3 different potentials, minus 250 millivolts, plus 250 millivolts, and just no potential at all. That's open circuit potential. Okay, so there we're going to apply these 3 different potential conditions. And what we're expecting to see is actually the carboxylate formation with the butanol formation. And so what we are expecting, of course, is that this reaction should be enhanced by electron withdrawing groups. So we're expecting this plus potential should accelerate this reaction, yeah? Whereas the minus potential should slow it down. Do we see that? We need to monitor the reaction progress, of course. And that's actually very convenient that this, this ester here has actually a very convenient peak in the surface-enhanced Raman spectroscopy. Okay, so surface-enhanced Raman spectroscopy is really great for this because we, of course, have a gold surface. That is actually a great surface for SIRS. And so we can clearly see actually this ester-related peak at around 1700 wave numbers. And so we're going to monitor that peak. So here are the results. Before hydrolysis, we clearly see the ester intact. Yeah. So if we apply no potential and cook this thing for a day, almost all of it is gone. Right? If we apply 250 millivolts, it's actually gone completely. Actually, if we apply 250 millivolts, we don't even have to wait a day. It's gone within an hour or 2. Okay. Most remarkably, if we apply a minus 250 millivolts potential, that ester peak is still there after a day. Now, at the beginning, I couldn't believe this, right? Because after all, what we're doing is we're taking an ester, we're exposing it to a 3 molar potassium hydroxide solution. Yeah. I might actually ask, how in the world can an ester survive this, right? It's 50 degrees. And so I had my student run this experiment for a week, right? And it's still there, okay? And after a week, if we now actually switch off that potential, then of course it's gone within a couple hours. Okay, I was very amazed. And so we thought, well, this maybe we found something here. Maybe this is actually really interesting. Should we publish this? I told my students, of course, we are a catalysis group. I like catalysis. I said, you know, let's do catalysis. Okay, let's show that we can do catalytic reactions with this. And the immediate idea is, of course, let's immobilize the catalyst onto the gold electrode and tweak its activity. That's, of course, the most obvious strategy to go. Well, we quickly found that the gold electrode is not ideal for this. Why not? Number one, the thiols, of course, the thiols, when they onto the surface, become actually thiolates, yeah, S minus. Yeah. And so when you charge up the surface, yeah, at around 450 millivolts, and so this number is actually for our thiol, but depending on what thiol you're using, that number can be somewhere between 300 and 700 millivolts. So at some point when you apply a negative potential, the self-assembled motor layer will actually come off, right? So they will just, you know, the electrostatic repulsion between the thiolate and the negative surface will at some point overcome actually the autophilicity of the thiol, and so you will just lose your self-assembled motor layer. Another serious problem is that even if you roughen the surface and you make actually a complete coverage of the surface, you've seen actually how little that surface is that I showed you on the gold bar. The catalyst concentration, the effective catalyst concentration that we can get into a reaction vessel is too low, right? Because the gold surface is just not big enough. The obvious solution to this is obviously to go to a carbon electrode and then attach the catalyst actually covalently, because carbon electrode surfaces can be gigantic. But now that's immobilization is of course possible, but it's non-trivial. And we cannot do a surface-enhanced Raman spectroscopy to test this. So we said, you know, this is a tough problem to solve. And one day we've been agonizing about this. And one day my student comes to me and says, "Well, we don't think we have to solve this problem." They said, because if we want to do a catalytic reaction, and we want to convince organic chemists that this is useful for anything, what is the reaction that we should pick? Now, the palladium catalyst Suzuki-Miura cross-coupling will probably be one of the top choices for this, yeah, because it's very robust, it's very useful, right? Industry runs this reaction all the time, right? Nobel Prize was given for this. This is actually a great reaction to do. And so my student says, well, of course, the way this works is, of course, that you start out with actually an aryl bromide, for example, an aryl halide, but aryl bromide is a good substrate. And then you actually have this boronic acid variant, yeah? And then what you're doing is, with palladium in solution, what you're doing is you are doing the oxidative addition that we just talked about to activate actually this, this aryl halide bond first. That's actually the first step. The first step is oxidative addition. And then, so that's actually what it is. You do actually oxidative addition to bring the palladium in here. And then the next step is transmetallation to actually activate this actually boron carbon bond to actually place 2 phenyl moieties on palladium. And then what you do is reductive elimination to make the carbon-carbon bond, and you reform palladium 0, and then you actually make the biphenyl. And this palladium 0 can actually now start another reaction. My student says, well, instead of actually worrying about immobilizing palladium, why don't we immobilize the aryl bromide with an thiol at the end? Because then we'll have a monolayer on the gold surface. And when we do the first step oxidative addition, then we actually have the palladium 2 on there. And even though we don't really know the mechanism exactly, right? So actually, you know, when I started this, I thought the Suzuki-Miura cross-coupling must be understood completely, right? So I thought that mechanism is actually settled. I have discovered now it's actually not, right? It's there's still quite a lot of disagreement, but it appears that everybody agrees that the first step of the Suzuki-Miura is the oxidative addition, and the oxidative addition with aryl bromide, everybody seems to agree is not rate determining. Okay, so and that's really fast. So I think, okay, what we can do is we can immobilize the aryl bromide through this thiol onto a gold electrode. If we expose it to palladium in solution, the palladium will actually become palladium 2 and then immobilize on the electrode. And since the next step, either the transmetallation or the reductive elimination is rate determining, we should see a difference in rate if we apply a voltage. Okay, so we were encouraged by this. So we actually looked at the resonance Raman spectroscopy of the substrate alone, and we can clearly see the aromatic peak in the source here, and there's actually the aryl bromide peak, and there's actually the sulfur peak there. Okay, so then we feel now actually for reference, we actually make the biphenyl, and then we can see there's still the same thing, but we see now a new peak appearing for the second aryl, and that's a little bit higher in wave numbers than the original peak. Okay, so we know what to look for. So this is actually what we ended up doing. We actually have now the aryl bromide immobilized on the surface. We add the palladium to the solution, and then this time we're going to probe 4 different conditions: minus 150 millivolts, 0, so that's open circuit potential, plus 150 millivolts, plus 300 millivolts. Okay, and the reaction conditions are the standard Suzuki-Miura conditions. There's palladium, and then we add actually some phospholigands to it. So nothing special here. Here are the results. With we see the starting material. So I told you actually here's the phenyl vibration. And then when we now, at the beginning, when we started this, we didn't actually know what to expect. We didn't know whether the negative potential should actually make the reaction faster or the positive potential. We didn't know, we just wanted to look at it. So it actually turns out when you have the starting material and you apply 300 millivolts, we get a little bit of product, okay? And so we are measuring after, I think, 12 hours, okay? 25 degrees Celsius, 12 hours. After 12 hours, and 300 millivolts, we are seeing a little bit of product. With 150 millivolts, we see a little more. With 0, we see even more. And with minus 150 millivolts, we see most, okay? So what we found is that the plus potential inhibits the reaction and minus potential enhances the reaction. And it actually turns out that this is exactly what John Hartwig reported many, many years ago by actually just doing a very similar palladium catalyzed Suzuki-Miura and then using bromide, aryl bromides, where he actually had replaced actually at this position with various functional groups. So we are reproducing the same trend that Hartwig actually saw. So the most important, I mean, I don't even want to get into what this actually means for the Suzuki-Miura cross-coupling reaction, even though we could actually think about what this means for the mechanism, but that's not the point here. The point is that this experiment shows that even for a catalytic reaction, applying a potential, we can control the rate of the reaction. Okay, all right. Okay, so we had two examples. We wanted to submit this really as quickly as possible. I was afraid that I would get scooped because I knew this was actually a big deal. So I wanted to publish this in Science. And so last year we submitted these two results. So the Suzuki-Miura and actually the ester subpolitification reaction. We wrote that up and actually submitted to Chem Archives. This is actually this new manuscript depositing system that that the American Chemical Society has. So that came out in the spring of last year, and so we actually have added one more reaction that I'll tell you about, and we submitted to Science. And now it took us a year and a half because the reviewers actually really liked it, but they wanted us to do some more stuff, so we did. So now it's as of actually 3 weeks ago or so, the paper has been accepted. We are making the figures now a little fancier so that Science will like it. So within the next month or two, maybe 2 months or so, this should come out in Science. So last thing I wanted my students to show me before we submit this to Science is I wanted to show that we can actually change the potential in the middle of the reaction and control chemical reactivity that way. Oh, there's a question. How is the reactivity on gold surface compared to those once in solution? The reactivity trend is the same, yeah? But of course, when you mean how is the reactivity on the gold surface compared to solution in terms of yield, the problem that we have now is, of course, that the gold surface has a very low concentration. Yeah, so I've shown you that the reactivity trends are exactly the same, right? So we can reproduce John Hartwig's Hammett study on the Suzuki-Miura. But what we cannot show you right now is, of course, this is a proof of principle study at the moment. We cannot look at yield yet because I can't just get enough stuff in there, right? So if we have time, we have actually some new ideas and we have new results where we think we have solved that problem. But so that's actually carbon electrode. We found a way of actually using a carbon electrode to immobilize and get a lot of stuff in there now, right? But those are, how the reactivity in general compares to solution. That's actually studies actually forthcoming, right? Okay. All right, okay, so I wanted to show, okay, there are a lot of questions. I have about 5 minutes or so to finish this story. Let me actually finish that and then we can get into questions, okay? All right. So the last part that's actually in the Science paper is I wanted to actually switch potentials and see whether we can do this. And this reaction looks a little bit constructed because it is, but bear with me. So the reaction that we came up with where we wanted to show the switching of potential in the middle of the reaction is actually a DCC coupling reaction, where this is actually a dicyclohexylcarbodiimide coupling reaction. The reaction is very simple. We start out with actually a carboxylic acid. And in the presence of actually this DCC, this dicyclohexylcarbodiimide, we can actually couple this, carboxylic acid with an amine in this condensation reaction. The way this actually works is the first step is the carboxylic acid attacks actually this carbodiimide to make actually this adduct first. And then the amine actually attacks this carbon here, right? Now this is actually you see, this is actually a nucleophilic attack onto this carbon first. And then next step, it's actually a nucleophilic attack of this amine to this carbon, yeah? So the first step electron donating groups on this carboxylic acid should actually increase the nucleophilicity of this carboxylic acid, and that should actually enhance the first step. Yeah, and then in the next step, however, having actually electron donating groups on this component is going to be bad for the reaction, because now this carbon here needs to act as an electrophile. Yeah? And so the idea is now it would be great if actually this moiety would be attached to something that's electron withdrawing to actually do this, to make this reaction work. We actually figured out that without any gold surface, if you just have an alkylic carboxylic acid with an amine and DCC in there, this reaction actually needs 16 hours and actually 50 degrees to finish. We wanted to see, can we actually switch the potential in the middle of the reaction and make this reaction happen at room temperatures? And sure enough, what we can do is we can attach actually this carboxylic acid to the gold surface. We apply actually a negative potential first, minus 300 millivolts. And then what we see actually is within something like 5 minutes, we can actually see the surface covered with this stuff, okay? So very clear signal of actually this at that point. And then if you actually keep the potential at minus 300 millivolts, nothing happens. It sits there and just stares at us for all day. Now what we do is we switch actually to minus 300 millivolts, and then we see actually a new signal that we actually now have assigned actually to this species, where of course this attacks here, this DCC actually takes this oxygen with it, right? Goes away, and then you make this product. And so with this switching, we can complete this entire reaction within something like 30 minutes. Okay, all right. So there are the reviewers, the science reviewers actually made us actually work this out in much greater detail. So when the paper comes out, we have done much more work on this potential switching. Okay, let's, I don't want to summarize. I'll just tell you what we can do with this, where we are going with this. I'm trying to take this actually to gas phase catalysis, right? So the idea is we'd actually have a surface that we can charge up, and then we'd actually have catalysts actually on the surface. Why gas phase catalysis? Because the induction window is going to be gigantically wide, and this gas phase catalysis is usually very difficult to control, right? So we think actually we can make some impact there. This is really asking for flow reactors, because the catalyst is of course already immobilized, so we can imagine making small modules where we can actually put this into flow reactors. That would also mitigate or actually help with this concentration problem. I told you the concentration issue on the surface is actually serious. If we actually have flow reactors, that would actually solve a lot of that problem. So we're actually looking very heavily into flow reactors. This reaction orchestration that I talked to you about through voltage sequence, we have shown one case where we can actually switch the potential in between to make this work. I'm very excited about this, because that will get us, I think, into an entirely new area of catalysis, because you realize the best catalysts are not the catalysts that do step one very, very well, right? Because then usually a catalyst that does oxidative additions very well is usually horrible at doing reactive elimination. So the best catalyst that we have currently available is usually something that makes actually something in between, right? It's not the great catalyst for oxidative addition. It's not a great catalyst for reductive elimination, but it's the best at doing both. With this new technology, with this reaction orchestration, we don't need that. We can actually, just make actually the first step highly efficient, and then usually we will be stuck, but we can just switch the potential to actually drive the second reaction. I can spend the next 10 years of actually exploring this chemo, regio, and stereoselective reactions, where people have shown that we would change the functional groups and actually change the electron density at the reaction center, that you can actually change chemo, regio, and stereoselectivity, right? We can actually just go and actually look at all of those, right? By switching a potential. Imagine a reaction where we would actually have one catalyst. If you want the R product, you apply negative potential. If you want the S product, you just apply a negative potential. Wouldn't that be great? I'm quite excited about the super electron donating and super electron withdrawing groups, because we can actually do these new catalytic reactions. Conventional function groups will not allow. Okay, so this is my group. I'm right here. This is actually what KAIST looks like. And that's a bridge that we have in Daejeon, and that's some Buddhist temple. Okay, I think I have 10 minutes left. and I'll start answering your question. Thank you very much.
Very cool. Thank you, Muki. Okay, yeah, we do have 2 questions in the chat or in the Q&A section.
Yeah, so one question that somebody had asked is, in which quantities are you already working? So with the gold electrode, we've calculated that the concentration is in a picomolar, right? So that's, of course, completely unacceptable. So that's actually, the picomolar concentration is good enough for the proof of principle, but it's not going to be good enough for the real things. Now, what we've been working on now is actually making a carbon-carbon bond, right, on the surface. And so we can use now, and we have actually figured out a way of doing that now. So we can get now about, what is it? We calculated about, we are now at about 0.1 micromolar. That's still low, I know, but it's actually much better than picomolar, right? So now if we take, so what we've been doing now is if we put actually a catalyst on there that is highly active, yeah? And we found few examples. Okay, I'm not going to tell you now here because it's not published yet, but we found we can actually put some transition metal catalysts on there at concentrations of micromolar or where we can get yield. And we can show the first preliminary results actually show that we can actually do it. So that's actually forthcoming probably by end of the year. Okay.
Okay, and right. I was wondering about the linkers. Do you think you can take rather long linkers without actually breaking the bond? Or what would you imagine, how high would you have to go with voltages if you needed a C4, C6 linker or something like this, until it actually shows influence at the end of the
great question. Chain. So what you're asking, of course, is the linker is going to be actually a big issue. Can you see my screen?
Yes. Okay.
So another study that, so I've now put something like 25 students on this, yeah. And so what are going to do about here? The linker is, of course, critical, yeah. So some of the questions that we're exploring is so I've shown you examples with these aromatic linkers. And we chose that, of course, because the inductive effect is expected to be maximized through this aromatic ones. We are actually, of course, looking at the aliphatic ones, right? So when I showed you the DCC coupling, there actually the carboxylic acid was actually on an alkylic linker. And we can see already that the mitigation of inductive effect is much, much less pronounced. So the aromatics are, of course, better. Yeah. Some of the questions we're studying again is actually, what about having the same thing with 2 or 3 linkers? Yeah. So is this additive? If you actually had another sulfur group here, yeah, at the not only at the para position but at meta positions, or if you actually instead of having only 1 sulfur linker, what about having 2? What about having 3? Right. So of course, with functional groups, if you actually have 3 methyls, these inductive effects are additive. Yeah. Is this additive here? We don't know. We are trying.
No.
Right. And then, of course, the other question that we need to actually do is we need to be a little bit careful here, because sometimes actually, if the linker is too long, the attached molecules may be wrapped around and actually get contact to the surface. Yeah. So of course that is okay later if the reaction works, but at this study state, at the state where we want to study this mechanism, we don't want the linker to be too long that it wraps around and actually just lies flat on the surface. Yeah. So those things we have to study. Okay. There's another question that says, do you also take German PhD students? Of course, I love German PhD students. So my group is gigantic. We are still looking for students. So if any one of you actually have interest coming to Korea to work for me as a PhD student or as postdoc or whatever, you know, I'm very open to this. Email me and we can actually talk about it.
Very good. I'm just getting someone a job right now. Nice. Yeah, I was thinking in a certain direction to my own research. Do you think one could possibly attach, say, both ends of a more or less linear molecule? Like, could we possibly investigate something like push-push or pull-pull effects on allenes if we attach them on both sides to your surface?
Oh, absolutely.
Yeah.
Absolutely. So of course, you know, we're at the very beginning, right? Because this is a new way of actually just, I mean, I'm not inventing this, right? Because this is basically the molecular version of the Stark effect, right? So physical chemists have known for a long time that when you change the voltage, that the electron density on the surface changes and the chemistry on the surface changes. So all I'm doing here is I'm attaching a molecule to the surface, and I'm actually constructing the Stark effect analog on a molecular level, right? And so any kind of the games that we play, right? So one thing that we are also excited about that we're actually looking at is, since I'm an inorganic chemist by training or by feeling or whatever, can we actually control the electronic structure of the transition metal, right, by applying voltages? Of course we can. We know that we can actually, I should be able to do spin crossovers. If you can imagine having actually a transition metal that actually has a high spin, if you change the voltage, you're basically doing the same thing that people have been doing by functionalizing their ligands. So at some point, you should be able to actually trigger spin crossovers. Another thing that we're exploring is, could we actually attach an iridium or some organic dye, that emits light, onto a surface and change its color? We should be able to, because you know that you can take this iridium phenolpyridine compounds, that are usually red, and if you put actually trifluoromethyl groups at the right position, this thing turns blue. Can we do that? Now that would be really neat, because then you wouldn't actually need to, we could actually, I mean, I'm in Korea after all, Samsung is desperate for new devices, to make actually displays. Why do we have to have red, green, blue dots? Can we not have one and then actually apply a control voltage to change its color? So that would be a completely new design of an OLED device. We're looking into that. So there are, of course, many applications for this.
Very cool. Thank you very much. So then we would head on to the next point. Thanks for your talk. It was amazing.
All right. Thank you very much, guys.
Right. So we still couldn't find Stephen Hashmi. Sorry about that. What will happen is I will see that I get him to take the talk as video and send an email out to you so you can watch it on demand. Then now our schedule is a bit shortened. That's why I would just go with 5 minutes break now before we head on to our last speaker instead of the 15 minutes, and then we will finish at 7:05. See you again in 5 minutes, guys. All right, welcome back. And let us get to our last speaker. That is Jan Wenz. Jan did his PhD in Heidelberg with Professor Garde. Jan, you can start your video now.
Yes.
Hi. Cool. Jan did his PhD in Professor Garde's group in Heidelberg, and then moved on to a short postdoc with Rebecca Merlin at Cardiff Uni before joining the Department of Molecular Imaging at the Uni Hospital of Ulm, and now moved on and is an expert sales manager in a German pharmaceutical company where they commercialize radionuclides to provide cancer patients with good treatments. And now he's going to talk a bit about the chemistry involved in nuclear medicine. I'm looking forward to that. Stage is yours, Jan.
Yeah, thanks very much for the introduction. Just a short question. Did you say we will continue on 7:05 because I was expecting to start now. Hopefully everybody in the audience is up to that and everybody can hear and see me.
I wanted to say in 5 minutes, sorry.
Okay.
If I said 7:05, the video
Okay,
said
then
it
I will
ends
start
at
right now.
7:05.
Okay, so thanks very much. As this field is relatively unusual, oops. Wait a second, I want to at the laser pointer. As this field is relatively unusual, I want to share my experience I got for the last 2 years in this business, because working as a chemist in a hospital is not so common, and I want to share the experience I made in the last 2 years with you. So before I started in this business, I knew a little bit about diagnostic imaging. To get anatomical information, you can use X-ray for getting a bone scan, for example. CT is also possible to get a view into the organs and the tissue. MRI is also possible. For me, it was always just the hydrogen NMR in the body, and also ultrasound is possible. But all these diagnostic techniques are only used for anatomical information and not for molecular imaging. And for molecular imaging, I want to point out one important Nobel Prize in 1943 for the use of isotopes as medical tracers to study chemical processes. So as radioactivity is the most sensitive way to measure, you can use picomolar quantities to measure exactly. So this Nobel Prize could be seen as kind of the use of radioactivity as kind of a GPS tracer in for detecting chemical processes or metabolic processes. If you then, if we have a look on the radioactivity, gamma quant is emitted, and yeah, this could be seen if you not only have one nuclei, if you have more nuclei, you can detect every decay selectively, and afterwards you can get an image. If you attach the nuclei to the human body, you can make molecular imaging, and what is the most commonly used technique is the so-called SPECT. SPECT stands for single photon emission computed tomography. So it's a combination about a molecular imaging technique and a CT. For the CT, you get a scan of the body, and the PET shows you exactly where the radioactivity is. The gamma quants get emitted by the nuclei, which is at the beginning in a kind of excited state. You know these images from UV-Vis or from phosphorescence spectroscopy, but the only difference is here we are talking about a nuclei, and the energy is much higher when the excited state relaxes to the ground state. The most commonly used isotope is technetium-99. It has a metabolic meta-stable state. This is called an isomeric state. Then it decays by emission of a gamma quant with 143 kilo electron volt, and then it can be detected in the body. What is also possible is the so-called positron emission tomography. PET in combination with a CT, you again get the information about tissue, and in this case you have radioactive decay from element A, which has a half-life independently, but it emits by radioactive decay a beta plus particle, which is a positron, and ends in the element B. Beta plus stands for a positron, and this is the counterparticle to the electron. And whenever it collides to an electron, an annihilation is observed. An annihilation means transfer from energy to from mass to energy. Whenever counterparticle, antiparticle, and the particle collides. So in this case, as they have the same mass, they can be emitted. Two photons are emitted with the same energy. In this case, it's 511 kilo electron volt. And the nice thing is they are emitted in an angle of the 180 degrees. So if you have a positron emitting particle, you always have two photons that are emitted. So the resolution is much higher than compared to SPECT. And the most important radionuclide used so far is fluorine-18. So here I have kind of a timeline that could also be seen as the content of my talk. First in the 1930s, by the invention of the cyclotron, and 10 years later by the invention of the nuclear reactor, the stage was open for radionuclide production. And since then, chemists and radiochemists were able to isolate different radionuclides and use them in nuclear medicine. And with these isotopes, also this corresponding scanners could be used. So as we are talking, as it's a chemical talk, I will focus on the middle part of this slide. So where do we start? Normally, the chemist starts with the periodic table. In our case, or in the case for a radiochemist, the periodic table is the so-called Karlsruhe nuclide chart. What you have here is a list of all the isotopes that are reported in literature so far. And the first thing that's obvious is the color code. The color code stands for the nuclide mode, decay mode, and blue ones are electron emitter, red ones are positron emitters, and yellow ones are the alpha particle emitters. So whenever you have a defined starting point with the parent nuclide, it's like playing chess on the nuclide chart. So you decay as long or till you end up in a stable nuclide in the end. So whenever I will be talking in this talk about cold and hot chemistry, cold is just it's not correlated to the temperature. It will be just that we are talking about non-radioactive material. And this is where normal chemistry starts. And what we know from, I think everybody from NMR spectroscopy, we have fluorine, for example, and we have tin. And in both cases, we have different distribution of isotopes. In case of fluorine, we have only one stable isotope. This is fluorine 19 with 100% naturally abundance. In the black field, the number below the isotope number is always the naturally abundance in percent. In case of tin, we have 10 stable isotopes, and this is also, well, it's not a problem for the chemistry, but we will see when we do NMR spectroscopy. In case of fluorine, all our atoms are NMR active, spin 1.5, spin of a half, and in the case of tin, we only have 115, 117, and I think 119 is NMR active. So also in cold chemistry, isotope distribution is important, and it's even more important in the field where I work now. And what's also important is, what also is possible, we have stable radioactive elements on the Earth. The heaviest atom we have is uranium. And what you can see here, the black number in the black field is the naturally abundance in percent. So most of the uranium is uranium 238, but also uranium 235 is available. The reason why I mention it is because this is the starting point for the first isotope I'm going to talk about. This is technetium. We need for that uranium 235. And what we have to do is we have to enrich it a little bit, and in a nuclear reactor, we have to add to the nucleus a neutron. So whenever you can see this kind of notification, it's a nuclear reaction. On the first side, you have what you add, it's a neutron, and the next thing that happens is fission. So it, the nuclear kind of explodes, and you have many decay products. And in these products, we have about 5% of molybdenum-99. Whenever you have a radioactive element, the number below the isotope is the half-life. In this case, it's a half-life of 66 hours. What can we do with this so-called mother nuclide? We can isolate it, oxidize it, and bring it on the aluminum oxide resin, and there it stays fixed. And what happens then is it decays by emitting an electron to the technetium-99 metastable compound. Then you have on the resin a pertechnate, and both elements are in a so-called secondary equilibrium. So that means all the time when you have when the mother nuclide has a longer half-life than the daughter, you will have kind of an equilibrium at a certain time. So when we just have a look on the activity of the mother nuclide, we have a normal, as expected, radioactive decay. And when we separate those two elements at the beginning, the technetium activity will increase over the time, and at about 24 hours, we have the same activity of the daughter compared to the mother nuclide. And this could be used for building a generator. So what are we talking about? At the beginning, we have only molybdenum. After 24 hours, we have a certain amount of technetium. This is not as strongly bonded as the molybdenum to the resin, so we can elute simply by flushing with sodium chloride solution, and we can use the activity for chemistry. What happens next? On the next day, we can do the elution again. We have less activity than the day before because it's radioactive, and so on and so on. So every day we will get a little bit less activity, and the problem is at the end, we have after 4 or 5 days, we have only about 20% of the starting activity. So those generators could only be used for 1 week. Anyway, they are commercially available, supplied all over the world, and this is absolutely daily business in nuclear medicine. So what about the chemistry? As there is no stable isotope of technetium available, most of the macroscopic models were done with rhenium, some of them with manganese, but most of the things were done with rhenium. So NMR spectroscopy, X-ray structures, mass, IR, whatever you do from normal cold chemistry was employed and investigated with rhenium. Oxidation states from -1 to up to 7. For reducing, as we are starting with paratechnate, we always have to reduce it, and normally tin chloride is used for that because it's selective, sensitive, and non-toxic. And as you know from coordinations chemistry, sulfur, oxygen, nitrogen, phosphorus, carbon monoxide, also isonoitriles are used for ligands. Just to mention a few drugs. In blue, these are the brand names. As here we have a neutral 5-coordinated technetium peroxo complex. This is used for brain perfusion, also cardiolite. I think this is the most prominent one. It's a cationic complex. And here you have an EDTA derivative called DGPA. This is an anionic compound used for kidney scintigraphy. The nice thing about technetium chemistry is that it's almost quantitative. You don't have byproducts. You simply take the ligand starting material, reducing agent, and you add the solution. And that's the reason why so-called cold kits are used for the synthesis. So you have all the starting material in a vial. You simply elute the sodium pertechnate solution into that vial, shake, and for quality control, you perform a radio TLC, and then you are done. So that's pretty cool. And from the homepage of the International Atomic Energy Agency, I took this overview of what kind of organs or metabolic systems could be investigated. I don't want to discuss all the things in details because it's not really interesting for us. Everything is based on a kit synthesis, so you simply add the solution from the generator, and then you are done. That's pretty cool, but the chemistry or the important part for the chemist is not taken on site. So I would say the preparation is done on site in the hospital, but the chemistry is more or less done in a pharma company or the university. So the second, and in my opinion, more important part for us as chemists are the positron emitters. Those are the reds here on the periodic table, and the production could be seen as, again, as playing chess on the nuclear chart. So what we are going to do, as you have a positron emitter, you have to have in the nuclei more or an overview of protons. So we have to add protons to the nuclei, and whenever we are doing nuclear reactions, we want to start at a defined starting point, otherwise we get a mixture of all the isotopes. As I mentioned in the beginning, fluorine-18 is the most important PET tracer, and for that we need oxygen-18. If we have a look on the natural abundance of oxygen, oxygen-60 is more than 99% available in the nature. So we have to do an isotope enrichment at the beginning. This is performed by distillating water over years, and then you can enrich oxygen-18 water, and then you can isolate it from this crude. So this is really expensive, but it's really important because otherwise, when you're doing this reaction, adding a proton, get loss of a neutron, with oxygen-60, you will end up with fluorine-16, which is not useful for that. So where do we do that? Oxygen-18 enriched water is commercially available. It's expensive, but you can buy it. So you simply irradiate it in your hospital. Where do you get the protons? In a so-called cyclotron. This is a relatively big or small device. It has about the same size like a big NMR device. Quite expensive, about $1 million, but used in, I think, every bigger hospital. So this is where we get the protons from. And the most important isotopes for PET spectroscopy are fluorine-18 and carbon-11. And those are the two isotopes I'm going to talk about. So for fluorine-18, as I mentioned already, there are, as I mentioned, the first production route from oxygen-18. What you do is you start with oxygen-18 water, irradiate with protons, and then you get fluorine in this solution. So you have about 1 milliliter of oxygen water with a few atoms, picomolar amounts of fluorine, and you want to separate them. And this could be done by anion exchange. QMA stands for quaternary ammonium exchange resin. So you simply flash your whole produced solution through this resin, and then you can recycle the oxygen O18 water. And to isolate the fluorine anion from this resin, you have to elute with an aqueous solution of potassium carbonate. Then you can add cryptofix in acetonitrile to the solution, and then you need to get rid of the water. That's why you can use acetonitrile, because it's an azeotropic distillation in the end. So at the end, you have a highly reactive fluorine anion. This is the one route. The second route, what's also possible, is to start with neon-20. That's naturally abundant at more than 90%, so you don't need an isotope enrichment, and you irradiate it with deuterons. That's also possible with so-called low energy cyclotrons. By losing an alpha particle, you get fluorine-18 as well. The difference is you don't get it as an anion, you get it as fluorine gas. But it's so reactive that it will react and stay on the surface. So you have to add a cold carrier, fluorine-19 gas, and then in the end, you end up in a helium matrix with a mixture of F18 and F19. When we now compare these two routes, the first one is more efficient nuclear reaction. So you can, in a shorter time, produce more activity. It's high specific because you don't have to add a carrier compared to the second route. Here you have fluorine gas, which is pretty cool because it's open for various transformation. As it's an electrophile, you will always lose 50% of the activity, which is a big drawback. And with the high reactivity, you have a slow selectivity. And adding a cold carrier will also occur with a lower specific activity, which is really important for the clinical use. But anyway, both production routes are used, and I want to show you where. The first and the most important drug in the PET business is FDG. This is fluid desoxyglucose, where you have kind of a sugar, which is glucose, where the OH group is exchanged with this fluorine. At the beginning, this was also performed by fluorine gas, and we had here a double bond, but it was really, really unselective. And then in the greatest improvement was to use the cryptofixed version of the fluoride, and since then you simply have this SN2 reaction in a protected mannose precursor, and after deprotection with sodium chloride, you get rid of all these protecting groups, and then you have this sugar. So what is done is simply an SN2 reaction. This was improved in 1968, but it's still present, and this is done all over the world, I think, every day. The yields are between 50 and 80%, depending on the synthesizer. In 35 minutes, you can do the reaction, so that's really, really efficient. That's the reason why this is the most common F18 drug that is used. Here I want to show you two more examples, just what is possible. Aliphatic nucleophilic substitution is also possible, and it's also possible to make aromatic substitution, nucleophile substitution. That's pretty important, and I will come to that later again. The second drug, and this is my favorite one, is F-DOPA. It's an amino acid which could be used for detecting various transformations in the brain, mostly for Alzheimer's disease, but also for amino acid metabolism, for example. So what is used? Oh, I have a question here. I will answer that later. What starts is, here you start with an electrophilic substitution with this tin precursor. This is quite toxic, and the yields aren't that good. And it's the electrophilic part, but this was the first time it was possible to make this F-dopa derivative. And in the end, you had to get rid of these protecting groups by adding HBr or HI, which is not really good for which is not really good for daily business or routine production. So you need to handle fluorine gas. I already mentioned this is problematic. A few years later, a new route, a nucleophilic route, was investigated. In this case, you can start with KHF. The first part is the nucleophilic aromatic substitution, followed by a reduction of the ketone, of the aldehyde, then HBr addition, and then you need an asymmetric alkylation. This is done by in the presence of a chiral phase transfer catalyst, and this is really not useful for a routine production. Anyway, it was possible to synthesize this molecule, and from that point, I think the best improvement was done, and this is my personal favorite reaction. So you start with this nitro group, and at the arrow, you do a nucleophilic aromatic substitution with TBAF. Then you add MCPBA, you oxidize this aldehyde, then it rearranges, and after the deprotection with HCl, you get the unprotected phenols. Anyway, also you're using the nucleophilic route, which leads to a high specific activity. It was not possible to make it for the optimized production because there were, with every step, there's potential to fail, and that's why it's not used in daily business so far. But it's not only organic chemists that were interested in making these kind of transformations. Here are some of, I would say, highlights from organometallic chemistry. In 2011, the Ritter group published this palladium-4 complex. That was really interesting because here it was possible to exchange this pyridine derivative to this fluorine anion, and by adding this palladium-2 complex, it was possible to make here a reductive elimination under quite ambient conditions, and then you could isolate these kind of fluorine aryl compounds. The problem here is palladium-4 is really, really sensitive, and you had to work under absolutely anhydrous conditions. So it is interesting, but only from the academical side of view. 1 year later, the same group published these nickel complexes, and they are really, really interesting because this nickel-2 complex is stable. You can normally isolate them by a column chromatography. So they are air stable, they are not water sensitive. And the nice thing is it was possible to use aqueous fluorine 18 for the activation. And then you simply get a reductive elimination of these compounds. That's pretty cool. Aqueous medium, nickel-2 is really stable, but so far I have never seen it in clinical use. Could be by the toxic nickel byproducts. I don't know. So far it has not been used for clinical application right now. And just 2 months ago, there was a Nature publication where they used this precursor, this boronic acid, and in the presence of this copper catalyst with TBAF, they were able to make a nucleophilic aromatic substitution followed by a deprotection of the protecting groups, and then you end up with F-dopa. And as described in this publication, they were able to make a simple automatization of this. HCl deprotection is also possible for a daily production under GMP conditions. So I'm looking forward to see this application in a routine business in the future. I think this could be really, really promising. So so far, I just wanted to give you an overview of fluorine-18 chemistry. As not every drug is containing a fluorine atom, sometimes it's also necessary to change the isotope. And the second isotope I want to talk about is carbon-11. Carbon-11 is produced by irradiation nitrogen gas with protons. By losing an alpha particle, you get carbon-11. Nitrogen 14 has a naturally abundant of 99.7%, so you don't need isotope enrichment. And in the cyclotron, it depends on what is also present in ppm quantities. If you have hydrogen, you end up with methane. If you have oxygen, you end up with carbon dioxide. Carbon dioxide can be in the gas phase reduced on a nickel catalyst to methane. And from this point, it's also possible in the gas phase with ammonia on the platinum catalyst to end up with HCN, which is a valuable precursor. Also, it's really toxic, but from that point, you can do various transformations for amino acid or whatever. Carbon dioxide is more common, more important, and the chemistry is diverse, I would say. You can activate them, carbon dioxide with Grignard reagents. It's also possible to reduce them in the gas phase on a molybdenum catalyst to carbon monoxide. From there, you can think about various transformation with transition metals. And it's also possible to oxidize it with chlorine, and then you end up with phosgene, which is also really reactive and a useful precursor. When you're working in the lab, it's normally the best to start with methanol. So what you can do is you can bubble the carbon-11 in a THF solution or a diethyl ether solution of lithium aluminum hydride, and then you end up with methanol, and from there you add HI and you get a methyl iodide. And this is the most commonly used alkylating agent in the carbon-11 field. What is also possible is the gas phase transformation at high temperature with iodine, and this route is normally done for the standard routine production. So you start with carbon-11 dioxide, reduce it to methane, and then you do the gas phase reaction. And this takes about 12 minutes. So we are talking about a nuclide with a half-life of 20 minutes. So you are already losing by preparing the precursor a lot of the radioactivity. So you have to be really fast afterwards. And another important transformation of methyl iodide is the reaction to methyl triflate. This could be done just by taking the gas flow of this product through a silver triflate column. This takes a few seconds and increases the activity in the factor about 10,000. So sometimes this really makes sense. And on the next slide, I want to show you a few examples that are used in daily business in the hospitals. The first is the Pittsburgh compound. Here, the challenge is, these are all products with the alkylation of methyl iodide or methyl triflate. The challenge is always to differentiate between other polar groups. Here, it's the phenol group that's also a nucleophile. In case of choline, this was used for detection of prostate cancer. You also have two different potential nucleophiles, but no problem to handle with a good synthesizer. And the last example here is methionine. This is used for amino acid metabolism and detection of brain tumors. And the selective alkylation of the sulfur is performed by starting with a cyclic starting material at the beginning, and then you get this exclusive alkylation at the sulfur atom. It's also possible to do palladium chemistry, cross-coupling reactions. When you start with a tin precursor, you can do Stille reactions. If you start with a boronic acid, here's just an example where you can do a microwave-assisted Suzuki coupling. So this is also possible, and it's also possible to make nickel chemistry, but all these, I would say, nickel or transition metal catalyzed transformations are so far on an academic interesting level, not yet for routine or daily routine business in the hospital. But I think everything with transition metals could be really promising. And the last part I want to talk about are metal radionuclides. I already showed on the on my timeline scale that gallium is a really important radionuclide. and this is commercially available on a generator device. So where do we start? We start with gallium-68. This is naturally abundant. We irradiate it with protons in a P2N reaction, and then we have germanium-68. This is the mother nuclide. It has a half-life of 270 days, and this is done by a high-energy cyclotron. So it's not a reaction that has to be done in the hospital. This is performed all over the world, and then you can isolate the germanium, pack it on different metal oxides, normally tin oxide or every metal 4+ oxide thinkable, and then a generator is built where you can elute the gallium frequently. So the big advantage of these generators is that elutions could be done 3 times a day, and they normally have a shelf life of about a year. So you buy it only once, and then you can do everyday synthesis with gallium. But not only gallium, and you can do PET analysis without a cyclotron, because you don't have to have the cyclotron on site. The next isotope I want to present is lutetium, because lutetium is the most important therapeutic nuclei at the moment. We start with ytterbium-176. This has also to be isotope enriched, and then we irradiate it in a nuclear reactor with neutrons, and we get lost of a gamma quant. And then we have ytterbium-177. This has a half-life of 2 hours and decays to lutetium, which has a half-life of 7 hours. So you get an enrichment of 7 days. And in the end, you only have to separate the starting material from product, and you can recycle the isotope enriched starting material. The separation of lutetium and ytterbium is really, really challenging, and that's why only one company so far is able to provide it on the market. And at the moment, it's available as endorucin beta. It's 1 molar lutetium-177 chloride in HCl, and you can simply buy it, and you don't have to produce it on site. What's also possible is targeted alpha therapy. For that, you need alpha-emitting particles, color code yellow, and the mother nuclide for that is uranium-233. This was produced after World War II in the time of the Cold War for building bombs, and in the 1990s, the Russians and the Americans decided to separate the thorium from these stockpiles, and this is also the mother nuclide for building the generator of an actinium generator. Here we go. And now actinium is available as actinium chloride or actinium nitrate. If you are interested in how such a generator looks like, there's a nice YouTube video from Oak Ridge National Lab where they performed these separations. Just Google milking the thorium cow, and then you can, if you have 10 minutes over, I highly encourage you to have a look on this YouTube video. So now, why do we use these radionuclides? We are not doing catalysis, so the only thing the only recommendation of a ligand we have is to form stable complexes. And that's why we used the simplest, or if you have a look on an organic chemistry textbook, metal organic chemistry textbook, the first ligand you will be seen is the DOTA ligand, and this is a really high stable complex. So for physiological conditions, we need a log K which is higher than 19, and I had a look on the thermodynamic database for stability constants, and when we have a look, gallium is over it, lutetium with nearly 24 is also over it. For actinium, I didn't find any data, but or any reliable data. They are not here, but I've seen a PhD thesis where it was calculated at 20, so it was also a little bit beyond. It could be used, I know that, but I don't have the perfect data for that. The reason why I mention iron here as well is because iron impurities are the most problematic in this field. So the chemistry we are doing normally is in aqueous conditions, so oxygen is no problem, and but the problem is any iron impurity, because you cannot use, we are working mostly in acidic conditions 1 molar HCl, for example, and if you're using metal spatula or needles, for example, you will always generate free ions, and they are in comparison to your desired radionuclide. And yeah, that's the reason why you have to use metal-free or work under metal-free conditions. So yeah, DOTA is the ligand of choice for all these kind of transformations. And here are 2 examples of biomolecules that are currently used. On the left side, we have DOTA-TOC. This is used for the detection of neuroendocrine tumors. And on the right side, we have the PSMA 617. This was invented in Heidelberg in the DKFZ. And this rare derivative is selective for detecting prostate or going to the surface of prostate tumor cells. So both are used for detection with gallium and sometimes used with actinium if lutetium is not working, but lutetium is the radionuclide of choice for cancer therapy. And for both peptides, there are clinical trials running, phase 3. This is the last clinical phase before market authorization. In case of lutetium DOTA-TOC, it's called the COMPETE study, and the VISION trial is for the lutetium 177 and PSMA. So both products will be on the market, and they seem to be game changers in oncology. So this is really a really important field for also treating cancer and not only detecting it. And here on my last slide, I tried just to summarize. This is just a few radionuclides that are only used for therapy, nothing organic, just therapeutic radionuclides. And yeah, you'll see it's not only iodine or technetium what is done in nuclear medicine, it's way more, and in the future it will become even more. That's why we need chemists in nuclear medicine as well. So yeah, if you have any questions, I will have a look now and try to answer them. Feel free to contact me via LinkedIn. And yeah, thanks for your attention.
Very cool, thank you, Jan. Yes, we do have 3 questions in the Q&A section. Paul Jacob is thanking you for the great presentation and is wondering if, as a salesman, you mostly deal with commercial business and supply aspects. Is it actually an advantage to have a chemical background in such a job on a daily basis?
Yes, it is. At the moment, I'm mostly talking to technicians. They have absolutely no idea why they should use under metal-free conditions or work under metal-free conditions. It's really important to have this background when you're working in research, for sure. And then in sales, it's always good to know what you are talking about. We are not only selling this radioactive stuff. You have a normal sales guy has never been in the lab, so they do not know how to start the HPLC, to measure the pH value, for example. To have this background is really good and makes you really valuable in a sales team, I would say.
Good. We also have Martin Dietl asking what exactly you're working at Ulm. Okay, so he had been working in Ulm, but
I have
elaborate on the research that you did before, on the work that you did before.
In the morning I was doing FDG synthesis for the daily business, and then also research. I've done quite a lot. It was a mixture. I've done mostly synthesis, but also research. So one also important isotope is zirconium. And as you know, zirconium is not forming metals 3+ complexes. Therefore, DOTA could not be used. And that's the reason why research is ongoing on this field as well. This was, I think, a part of the half of my day, the research. Carbon-11 and zirconium were the isotopes I was working with. And the rest was daily business, mostly lutetium labeling for treating prostate cancer.
Very good. And next, next up, we would have a question of how would a typical workday look in the life of a chemist in nuclear medicine? And I think that's pretty closely related to what we had right now. So
yeah, but
a combination
the
of
day starts
research
at
and
5 o'clock in
production.
the morning. That's, I think, a really important point to mention, because normally the physicians want to start at about 8 o'clock, and the synthesis should have been done by then. So normally it could be not for the chemist, but for the technician. But as in the public sector, most of the time, the funding is quite limited. Also, the chemists or I would say the people with higher salary have to do the synthesis. So you can calculate, if you want to start in this business, most of the syntheses are done before 8 o'clock in the morning.
Yeah. How long would they usually be active? So you need to prepare everything before the patients arrive, yeah?
For carbon 11, you can at maximum use one synthesis for 2 patients. If you are doing fluorine 18, for example, FDG is done once a day, could be used for the whole day. The same for technetium, they do 1 synthesis a day. For gallium with a half-life of 68 minutes, it always depends on the starting activity, but in gallium you can use maximum 3 patients, and the measurement is about 30 minutes. So every 4 hours you have to do you have to restart a new synthesis. And in most cases, time management is the most important part in nuclear medicine. Not only for the chemists, so for the whole sector, time management is really, really important, because normally you start with 2 gallium patients in the morning, then you have the FDG synthesis, then the next gallium patient and the carbon 11 patient will be measured. So it's quite, you need a sophisticated supply chain. Okay,
very good. I just got notice from Stephen Hashmi. He apologizes. His internet is absolutely not working this afternoon or this evening, sadly. Let's see if we can get a video of that. And then there's one last question, which is a very good closing remark. So anybody who has ever been to one of my meetings live will know that I'm notorious for bringing free beer and wine to those. And Paul is asking if there will be any alcoholic beverages after the session, but sadly I cannot deliver them digitally yet. Technology is just not there yet. Sorry about that. All right, this was the recording of the virtual meet in DelocChem. I hope you enjoyed the video, and stay tuned for the announcement of next year's DelocChem. Thanks, bye.